Good afternoon, everyone. I'm Donghui, a recent PhD graduate from University of Edinburgh. I'm here to deliver this presentation on behalf of my PhD advisor, Professor Magford, who cannot be here today, cannot attend, sorry. And so our topic is structural health monitoring data analysis on two cable-stayed bridges in the UK and China. Today's presentation is simply divided into the temperature field analysis on concrete decks and towers, and also the traffic-induced deflection predictions using neural network models. First, some background. Long-span bridges play an important role in modern society. Most of long-span bridges were constructed after World War II in North America and Europe. In the US, the American Society of Civil Engineers publishes an infrastructure report card every year to assess the conditions of all American infrastructure. In their 2021 report, it was revealed that 42% of bridges were over 50 years old, and 7.5% are deemed as structurally deficient in this country. In the UK, the Forth Road Bridge, which is near Edinburgh, was discovered with truss and link failure in 2015, and combined with other factors like unexpected increasing in traffic, this bridge is now replaced by the Queensferry Crossing. Next, I will introduce something about the research target. The Forth bridges consists of 3 bridges connecting Edinburgh to the south and 5 to the north over the Firth of Forth, which is the estuary on the north of Edinburgh. Here is the overview of the 3 bridges. The red bridge is the Forth Road Bridge, the oldest among 3. It's a cantilever railway bridge. This bridge is considered as one of the symbols of Scotland and also a UNESCO World Heritage Site. In the middle is the Forth Road Bridge, which opened in the 1960s. It's a suspension bridge, but now it's only open to pedestrians, public transport, and cyclists. The other traffic are carried by the Queensferry Crossing, a 3-tower cable-stayed bridge with an overall length of 1.7 miles. It's now carrying the M90 motorway, a very important traffic link over the Forth in the central belt of Scotland. This area have over half the population of Scotland, so you can say that this is a very important bridge in Scotland. Both Forth Road Bridge and Queensferry Crossing are fitted with a structural health monitoring system, which provide continuous monitoring data about the bridge itself and its environmental and the operational conditions. The bridge in China is the NDB, formerly known as the Third Nanjing Yangtze River Bridge, opened in 2005, which is also a vital transportation link crossing the middle and lower Yangtze River, connecting the city of Nanjing and its Liuhe district. It's a double steel tower cable-stayed bridge with a main span of over 600 meters. A unique feature of this bridge is its 215-meter height, arch-shaped steel tower, the first kind among such long-span bridges. Next, when we talk about bridge maintenance, inspections are vital. Bridge inspections can be put into 3 categories. The visual inspections, which is the most comprehensive and normally used reliable method. And also the non-destructive testing, which use techniques like acoustic emission to assess the bridge conditions. And also today, what we are talking about is the structural health monitoring system, which use various types of sensors. Most of them are permanently fitted on the structure to provide the condition of the bridge. Here are some types of sensors installed on the Forth Road Bridge and the Queensferry Crossing. For example, there are about 192 sensors on the Fosford Bridge and over 2,000 sensors on the Queensferry Crossing. We can see that there are thermometers to monitor the temperature variations on different parts of the bridge, anemometers to give you the wind speed and direction on the tower, and dynamic wave motion system gives you the information of passing vehicles. Also, on the bridge itself, there are accelerometers and GPS stations, which gives you the displacement of the bridge deck, and also string gauges. These systems all generate huge amount of data. For example, 24 gigabytes of data on the Fosford Bridge and over 200 gigabytes on the Queensferry Crossing. And next, let's talk about the temperature field analysis. First, this is the sensor layout on the Queensferry Crossing, that they are installed on various parts, including critical locations of the deck, such as the mid-span, on the piers, also on the mid-height and the top of the towers, and also on the longest stay cables. Even though different sensors have higher sampling rate, some perhaps 100 Hertz, the recording sampling rates for all sensors are just 1 Hertz to save storage space. However, under extreme weather conditions, the data will be recorded at the sensor original sampling rate. On the Yangtze River Bridge, the location of the sensors are similar. However, they are stored in a higher frequency of 10 Hertz due to the smaller number of sensors on the bridge. First, we investigated the thermal-induced structural response on the Queensferry Crossing. We started by identifying the critical locations on the bridge by applying a unit load on the bridge finite element model using MIDAS. The unit load is specified in the Eurocode as vehicle load mode 1. The sagging and hogging moments are plotted here. For the girder section, we see that several locations have the relative large moments, such as the north and south auxiliary piers, and also on the south and north mid-span. Combined with the sensor layout on the Queensferry Crossing, we actually use the south mid-span section and the tower at mid-height and longest stay cable to study the temperature field. Similar approach was used to study the Yangtze River Bridge to identify its critical sections. Let's first have a look at the temperature field of the concrete deck, which is just on top of the deck section. There are 5 sensors installed in the cross section of the concrete deck. We can see that even for this small thickness, the temperature difference is between the top and bottom of the concrete deck is quite large, which the maximum reach 10 degrees Celsius, and normally it's distributed between 0 and 10 degrees. If we look at this time series plot, we can see that the difference is quite large in the summer months, indicating a strong solar radiation effect on the concrete during that time. Next, the temperature difference between the inner and outer side of the concrete tower was investigated. We were trying to use 1 year of data, but there was some data loss problem for the sensors on the tower. So you can see these large gaps. Also, the maximum temperature difference is 4 degrees. Most of them are only between 0 to 3, so it's smaller than the concrete deck. By comparison, on the Yangtze River Bridge, the temperature difference is larger, between 0 to 10, and with the maximum temperature difference reach 10 degrees. Therefore, the solar radiation on the Queensferry Crossing is not dominant contributor compared with the Yangtze River Bridge. With the information of 1 year of temperature difference, we can make estimations of the extreme temperatures for the next 120 years using this data. It's very important to verify the extreme temperature difference using the actual monitor data against the design code. Here, we used a method called generalized Pareto distribution, GPD. GPD is used to model the tail of another distribution, for example, normal distribution, which is, this method is widely used in extreme value estimation. Here is the results for the tower temperature difference on the Queensferry Crossing for the next 120 years. We estimate that it will reach 4.66 degrees Celsius. However, this this extreme temperature is not specified in the Eurocode. In the Chinese design code, it's specified as 5 degrees Celsius. So we can see that even in Edinburgh, the temperature difference is not very large. The estimated maximum temperature difference is very close to the Chinese design code. And my colleague Sean Shu was conducting similar research for the Yangtze River Bridge. In his research, it's actually discovered that from the monitor data, the estimation is actually larger than the Chinese design code. Next, we are investigating the thermal deflection relationship with neural networks. This plot gives the raw data of the displacement, vertical displacement of the midspan, and one of the temperature sensor readings from the deck. We can see that the displacement oscillates in a high frequency compared with temperature. That is because the displacement is due to a combination of both temperature effects and dynamic loads, for example, from vehicle and winds. So therefore, it's necessary to separate these dynamic loads effects from the displacement measurements. Here we use the wavelet transform to decompose the displacement signal. Here is the decomposed data. We can set the high frequencies to 0 and then reconstruct the signal. Only remain, therefore, in this procedure, the low frequencies will remain. For example, here are some comparisons of the reconstructed displacement data in the black line. And when we compare the temperature and displacement, there is a quite strong correlation between them. But also a noticeable time lag exists between them, indicating that the impact of temperature changes on the bridge displacement does not occur instantly. Furthermore, this time lag is not a constant value. This is the reconstructed displacement data using the wavelet transform and the temperature recordings. Next, we use a neural network model called the long short-term memory to map the relationship between temperatures and midspan deflections. Temperature readings are from both steel and concrete deck, and both ends of the cables, which serve as the input to the neural network. And we use the wavelet transformed GPS data as the output. The results shows that the LSTM, long short-term memory, is able to map the thermal deflection relationship, even there is a time lag between them. Next, let's discuss about traffic-induced deflections. This figure shows the average traffic flow daily variation on an hourly basis according to a document from Transport Scotland. The southbound is traveling towards the city of Edinburgh, so we can say that two peaks in number of vehicles corresponding to the morning and evening rush hour. For the southbound traffic, the morning rush hour is slightly busier than the northbound because people are traveling to the city for business and work. The evening is the opposite. The northbound is the opposite. On average, there are 80,000 vehicles passing the bridge daily. The dynamic wave emotion system are installed on the bridge entrance and exits. This table shows some examples of data from the system. We can see there are a number of axles of passing vehicles, the length of each vehicle, and the speed, and also the gross weight. However, there is a problem with this system. At the time we inspected the data, that it cannot record every vehicle passing the bridge, but the issue is believed to be resolved by now. By that time, only roughly 10% of passing vehicles are recorded. Therefore, we proposed a method to simulate passing vehicles on the bridge by using the traffic volume, vehicle attributes like speed and gross weight. We can derive a distribution for each class of vehicle on each lane based on the incomplete dynamic wave motion data. Here is an example using the trimodal fit. The trimodal fit consists of three normal distribution. So here you can see three mean and mode, and the weight of each normal distribution in the trimodal fit. With this trimodal fit, we can generate fleet, of vehicle. This is a proposed simulation method. We started by generating a fleet of vehicle at the entrance, then updated on a second basis based on two criteria, the car following model and the line changing model. This is the trajectory of the proposed method. Then we can have the simulated deflection at the south mid-span using the influence line from the finite element model. With this simulated deflections, we can also use the neural network models to make predictions. So we used vehicle attributes at the entrance as the input, and the mid-span deflections as the output. So we can see that the predictions are very accurate. So what's the conclusion is that the temperature difference should be considered in analysis for concrete sections. And the extreme temperature difference analysis reveals that extreme estimation for bridge tower thermal load is close to the Chinese design code. Therefore, a revision for the Eurocode is necessary. And LSTM is efficient in mapping both relationship between the temperature and deflection and the vehicle attributes and deflection in the middle span. I would like to say thank you to Data-Driven Initiative, European Union, and Screen Eagle to provide the fundings for this research, and Transport Scotland to provide data, finite element model, and documentation for our research. At last, it's a little bit promotion for our conference in Edinburgh this summer, the Structural Faults and Repair European Bridge Conference, which is taking place in June. This conference covers a very wide range of topics. I have several flyers of here. So it has the website and key dates. If you are interested, you can have one of these. Thank you.
A very nice presentation. Thank you.
Thank you.
I saw a lot of data you presented, and because of time, you probably couldn't present all of those. But I'm wondering if those data would be available to the public now or in the future. Thank you.
Unfortunately, this data is private to Transport Scotland. We have to make requests to them if they whether they want to release this data or not. So it's not public.
Thank you for an interesting presentation. I have when you are designing for a extreme temperature and base on statistics, but we have the climate change. Are you safe in using statistics for determining the maximum effect, or do you need to make other considerations?
Sorry, can you clarify your question a bit?
You told us about the extreme temperature that you anticipate in the future,
Yes.
But I guess you are basing that on statistics of the past.
Yes.
But we have the thermal change,
Oh, yes.
and then perhaps history is not the only way to go to the anticipation.
Yes, that's a very good comment and question. I agree. There are climate change and things like that. So the standard practice is to based on 1 year of monitoring data, but there are research to use perhaps 10 years of the past data. In that case, I think there would be a trend to indicating climate change and temperature rise. So yes, I agree. If you use longer time of data, the prediction would be more accurate.
Thank you very much.